Welcome back. We'll continue with our preamble into the finite element method. And you will recall that in the previous segment, we had started working with this linear one-dimensional partial differential equation, which was of elliptic type. Okay, and we'd written out this differential equation. We had also motivated it in the context of elasticity, and also looked at how essentially the same partial differential equation arises in other problems, right? We looked at heat transport as well as mass diffusion. Okay, we'll pick up now, but we'll focus on the PDE itself, right? So the topic of this segment is what we call the strong form of the partial differential equation. Okay? So the strong form of a linear PDE for partial differential equation of elliptic type right, in one dimension. Okay. Now, let me write the PDE, and this is the same PDE that we were working with in the previous segment, but let me put it down now. Okay. So what we want to do is the following, right? We've set ourselves the task of finding u, function of x, given certain data, right? We're given u naught, we're given ug, or we're given t, right? And remember how we qualified the difference between ug and t. Ug would be the Dirichlet boundary data, and t would be the Neumann boundary data. Okay, we're given these. We're also given the function f, function of x, and the constitutive relation and that constitutive relation is sigma equals e u comma x, right? Given all of this, what we want to do is, we already said that we wanted to find u. So we want to find u given all of this information such that the spatial gradient of sigma plus f equals 0 in the open interval 0, L, okay, with boundary conditions the boundary conditions being u at 0 equals u naught, and either u at L equals u given, or sigma at L equals t. Okay, this is our specification of the linear partial differential equation of elliptic type in 1D. Now, we call this a strong form of the equation, right? That's new terminology that I've introduced. We call it the strong form for two reasons. One is that if you look at the PDE itself, you will observe that the PDE has been specified to hold essentially at every point in the interval of interest, right? When we say that d sigma dx plus f equals 0 in the open interval 0, L, we're specifying that that PDE has to hold at every point, right? So in a sense, that is a strong condition. We're saying that at every point we want it to hold. Additionally, you observe that when we account for this constitutive relation, right, what this implies is that if we substitute that constitutive relation for sigma in the partial differential equation, what we get is the following form, right? We get d dx of sigma, but sigma itself is E du dx plus f equals 0 in the open interval. Now, if you observe that term, what we see is that there are two derivatives effectively on the field of interest, right? There are two derivatives implied here on the primal field U, and that is a slightly strong condition because really for this equation to make sense classically, we do require that U should be a function of a type that allows us to take two derivatives, okay? As you may imagine, if U is not a terribly smooth function, if it has discontinuities and so on, if even worse, right, if it has delta functions, right, a Dirac delta function in it, there are certain difficulties we are going to encounter with taking two derivatives of it, okay? Right? And so what we are doing here is we require so-called strong conditions of what I will loosely call smoothness. Okay, on U. Right, and why is this? Because the strong form, and I will capitalize it here to emphasize that for now it's something special to us, right? We require strong conditions of smoothness on U of x because the strong form has two spatial derivatives. Right? And there is also this idea that we require it to hold pointwise. Okay? So we require the partial differential equation to hold pointwise in the interval of interest. Okay? These are the reason for which we call this form of the equation the strong form. All right? And this, of course, is the classical form in which you have seen partial differential equations posed up to this point, assuming, of course, that you do not already know something about the mathematical background to finite element methods. Okay? All right, so this is the strong form of the PDE of interest, and of course we observed in the previous segment that it models elasticity, it models heat transport, mass diffusion, and so on. What I'm going to do now in the next few minutes is sketch out for us the approach to an analytic solution. Okay, and I say just sketch out because I'm not going to actually produce an analytical an analytic solution, but I will point us in the direction of how we would proceed. Okay, of course I'll be using the fact that this is all in 1D, so it makes life a little easier for me. Okay, so let's now look at an analytic solution. Okay. The approach is very straightforward, and you probably already know how I'm going to approach it. it is to simply integrate them. Okay, so we have d dx of sigma equals minus f, right? And I did that by just moving f over to the other side. Let's just integrate. Okay, so we integrate this. Now I'm going to integrate this from 0, not all the way up to L, okay, but I'm going to integrate this from 0 to say y, okay, and here d dx, of course, and here I have integral of f also over the same limits, right, 0 to y dx, right, where y belongs to the open interval, sorry, it belongs now to the closed interval, right? Y belongs to the closed interval 0 to L. Okay. Importantly, we do not actually, in solving this PDE, we do not want to integrate all the way up to L, right? Because we want to maintain a general solution applicable at any point, right? And that's why we don't take the upper limit all the way up to L. Okay. This again is completely straightforward, right? So what we know we get from here is we get sigma at y minus sigma at 0 equals minus integral of f dx over the limit 0 to y. F in general is, at this point, I mean, it's not quite unknown. It's data which we would know if we set out to actually solve a problem, but I want to leave it general. I do not want to assume a particular form of f or anything, right? All right. So we have this, but then we realize that what this implies is, of course, this, right? It is that E u comma x evaluated at y minus E u comma x evaluated at 0 equals minus integral 0 to y f dx. Okay, so that's what it implies for us. Okay, and you see how I get this last line by simply making the substitution for the constitutive relation for sigma, right, at the two limit points. Now, in what is actually somewhat of an abuse of notation, let me simplify this to write as, let me simplify and write this as E du dy equals minus integral 0 to y f dx plus E du dx evaluated at x equals 0. Okay, right? Okay, so and now you know what the next step is. Well, we need to do one more integration, right? So what that does for us then is the following. So now we'll integrate this again. Now let's integrate from 0 to z, right? Or 0 to z, depending upon which part of the world you come from. Okay, so that becomes E, that the integral here is E du dy equals minus integral 0 to y of f dx, and then we're doing another integration, right? 0 to z dy. Okay, and just to make it clear, let's do this. Okay, and then we have another term here which is plus E du dx evaluated at 0. Okay, but this term also gets integrated from 0 to z dy, right? Okay, again, straightforward enough. What we get here, now note that, of course, E could be a function of position, right? So you're allowed to make E a function of position, so E could also depend upon Y, all right? So now when you do that integral, we know what we get. We essentially get, to make things simpler, let me forget about that particular dependence, okay? Let me leave things as they are. Okay, so let's suppose that E is a constant and we go ahead with the integration. What we get here is now E U at Z minus E again U at 0 equals everything that we have here on the right hand side, correct? So we have an integral 0 to Z, integral 0 to Y, f dx dy plus integral 0 to z. Well, actually, this last integral can be made fairly simple now, right? Right, because it is just E du dx evaluated at 0, right, times z. Okay? So this is the final form that we get, and since we want to write this all as a result for u of z, we write it as 1 over E of integral 0 to z, integral 0 to y, f dx dy plus E du dx evaluated at 0 times z plus E multiplying u at 0 and close the brackets. Okay? So this is the final, the general form of our equation. Of course, I made things even a little simpler for us by saying that let's just assume that E is not a function of position. Okay, and if E were a function of position, of course, this would involve a little more. But just for the point of fixing ideas, I want to take this approach. Okay, now you observe that we have some unknowns here, but we know how to apply them, right? We would apply the boundary condition here. We'd apply the Dirichlet boundary condition here for u of 0. That is equal to u naught. Okay? That leaves us, however, with one more unknown, which is this. Okay? And this would be obtained by applying the boundary condition that we have at L. Okay? This term is determined by applying the given boundary condition, BC for boundary condition, at x equals L, right? X equals L, or in this case, Z equals L, because we are finally expressing this as a function of Z. Okay? All right. Now, if the boundary condition that we have at Z equals L is a displacement boundary condition, if it's a Dirichlet boundary condition, it would be straightforward to apply it. What if it were a Neumann boundary condition? Think about it. Straightforward, of course. It's trivial almost. If it were a Neumann boundary condition, we would simply carry out a derivative of U, right? And thereby that would allow us to apply the boundary condition, right? So if boundary condition at x equals L is a Neumann boundary condition, we first calculate or go to u comma z using that form of the function. Okay, and that will then allow us to apply the Neumann boundary condition, right? And then apply the boundary condition E u comma z at L. Okay, that will then allow us to determine this unknown. Okay. I also note now that I have just one sign off in this slide. I have a minus sign here, which I forgot to carry over, so let me just put it in here. Okay, that takes care of things. So this would be the general approach to getting an analytic solution of the strong form of the PDE that we're working with. Okay. The trouble with this, of course, is that we can do this only for very special forms of the forcing function f. All right. And furthermore, we did observe during the process that I simplified things by saying that E is a constant. Okay, I'm assuming that E is a constant. Does not always have to be the case. I assumed E were a constant to go through the process. If E is not a constant, it makes the process a little more complicated, right? And likewise, if F were some sort of complicated function. Furthermore, this sort of simple-minded approach or simplistic approach works only in one dimension, right? As we go up to higher dimensions, integrating up the equations of this form, this particular linear elliptic PDE, is not at all a trivial matter. Right? Exact solutions or analytic solutions exist only for very special cases. And what we're trying to develop here is really an approach to solve general boundary value problems, right? With general data in the form of F and E. So that's what we're going to go on to shortly, but we'll do that in the next segment. And we'll end this segment here.